We're going to follow the previous two recordings which talked about how to create a basic circuit by a slightly more efficient and effective circuit for our purposes. So we've got our power supply, our switch, our filament bulb. That's in pictorial view. We've got a much neater, much more organized version down here in symbolic view. Power supply of 9-volt battery, single pole, single throw switch here, and a filament bulb. So that's a standard sort of torch circuit. You would find that in any torch where you flick the light and away you flick the switch and away you go with the light. But very often we actually use low voltage, low power components as well. So I'm going to show you now. We're going to construct, using our pictorial components first, we're going to construct a light emitting diode circuit. Okay, so I'm going to choose once again a battery. I'm going to choose again a switch because we're going to need something to turn it on and off with. I'm then going to choose a red light emitting diode, and I'm going to connect those items up. Okay, now this is going to give me a slightly false reading when I create this circuit because there's actually a component missing, but I'll talk about that component in a second. Polarity is where you have a positive and a negative, and many electronic components have polarity. That means they've got to go around in a particular way. The LED is the most obvious example of that in this circuit, where we've got a positive leg and a negative leg. Now on a real LED, you can see a short leg and a long leg. The long leg is connected to the positive rail, the short leg is connected to the negative rail. Okay, so if I connect this circuit up, we should see exactly the same as we've got here. That's the same circuit. If I flick the switch, my LED comes on. Now in reality, 9 volts flowing through an LED are going to cause us a problem. So I'm going to put another component in position. In Yenka, to remove the line, to remove a connecting wire, you just select it and then you press delete to remove it. I'm going to open that switch before I put my component in. And then I'm going to put my resistor in. Okay, so this resistor is now sitting in position. It's all connected up, and you'll often have seen these in any circuit you look at. They're in every circuit, and they're in this case used to protect the light emitting diode from too much power. Okay, so if I now flick the switch on, power flows through here, and we've got 10.44 milliamps of current flowing. Okay, we've still got 10.44 milliamps flowing. But I don't know if you notice the difference before and after the resistor. I'll just move it backwards so you can see. 10.44 milliamps, and we've got 9 volts flowing, or available as potential energy. After the resistor, we've got 10.44 milliamps flowing, because that's what the light emitting diode is drawing in order to light up. But there are only 1.9 volts available as potential energy, because the resistor has acted as a block. So it's reduced the amount of power getting through. Okay, I'm going to build that circuit again in symbolic terms. Remember, symbolic circuit construction is much easier to read, much simpler. So I'm going to do the same thing. I close my pictorial components and use my symbolic ones. So here we go: a 9-volt battery, a single pole, single throw switch, a light emitting diode. Okay, and I'm going to connect those up. Now, if you end up getting followed around by a wire, you can click to release it. So at the moment, we've got the potential power of 9 volts coming up to the switch. The switch is open, so no current is passing. It comes down here to the light emitting diode, but no current is passing, so it's not on. It's not turning on. Can anyone predict what will happen when I flick that switch? I'm going to close it. Bang. Okay, what that represents is the damage that's caused to the LED. Can anyone remember why? What are we missing? What's the key component that's not there? Right, I'm going to put it in. I'm going to just fix that. I'm going to open the switch. I'm going to fix the LED by clicking on the spanner. Then I'm going to select that line and press delete to remove it. I'm going to put in the magic component, which is over on the left here, the resistor. Okay. Now in order to make that fit, I'm going to just move that out a little bit, and my resistor is going to sit in here. To rotate a component in Yenka, you select the component, click, 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 and you get this little circle appears above it. I'm going to rotate it. Okay. Okay, so we've now got in our circuit a 680 ohm resistor in series with our other components. So the power flows from here, 9 volts available. When we close the switch, without blowing up, our 9-volt battery is providing power to the LED, but it's limited by the resistor. So let's have a look at what our numbers are telling us. We've got 10.44 milliamps flowing and a 9-volt supply. Same after the switch, same before the resistor, 10.44 milliamps, 9 volts. After the resistor, we now have 1.9 volts. Same amount of milliamps are passing through the circuit to light the bulb. Now actually this is too high a value of a resistor. That symbol that we're looking at there is omega, and the value of resistors are measured in ohms, OHMS. I'm going to reduce the amount of resistance by clicking on there, and that allows me to change the value. 470 ohms. And actually what we've now got is a much more kind of controlled limiting resistor that we could use without particularly dimming the power. Let's turn that up to a 1000 ohm resistor and see what happens to our LED. You see the amount of current diminishes, the amount of brightness diminishes. It's beginning to have an impact. 1000 ohms are beginning to prevent enough power. So we've only got 7.11 milliamps there. Let's reduce that down again to 470. So our bulbs come off. I wonder whether anyone can spot why. There's a little K has appeared there, and actually what that means is that it's 470,000 ohms. If I click on that, I can choose my single unit. So 470 ohms allow enough current to pass that we can light our circuit. In actual fact, sometimes I will use a 330 instead of 470. I'll use a 330 resistor, which gives us nice brightness but still limits the amount of power getting to the LED and damaging it. Okay, so in this configuration, that resistor is known as a limiting resistor. It prevents too much power getting to the LED. So what we have here is a 9-volt power supply. Power flows from the positive terminal to the switch. When the switch is closed, power can flow through the resistor to the LED, lighting the LED, and back to the negative terminal of the battery.